throughout because it's the same ideas brought up. But what I wanted to touch a little bit here is that about scale up. Okay, we talked a lot when we started about small channels, microfluidics, and we said from the beginning that there have been a lot of applications on analytical applications with the microchannels, but people have started considering also the use in production for process intensification. Once you get into that sort of area, then you have to start thinking what all chemical engineers have been thinking forever, which is scale up. Okay, everything works very well in the lab. How do I go? How do I continue? How do I actually bring it to industry? And it's a big discussion, and we are discussing it with industrial collaborators. And of course, there are questions, and it's not that we have all the answers, but it is good. It helps us focuses our minds to start thinking that it doesn't matter if something works perfect in the lab. If you cannot transfer it to the application, then okay, you have to look for something else. Scale up. So I will start with this graph. And as I said, some things come up again. How can we increase throughput? How can we actually produce more? I don't know. Do people have some answers here? Any thoughts from the audience on how do we increase scale production volume, let's say? Okay, yeah. Oops. I hope it doesn't change on its own. Yeah, scale out, number up. So we have one channel, works perfect. Let's use a lot of those. Any problems there? Distribution of
we have to consider the loss which are in consider. We try to simulate dynamic and
when you go scale up, like from a small to a big, yeah? Yeah.
to consider all the dynamic similarities come.
Yeah, all the types of similarity, physical similarities playing a role. So this is important. That's how people used to do scale up, try to keep some sort of similarity between the processes. So if you now have your small channels, one way to increase is what was mentioned, that you use more of them. And the issue there might be, somebody said that if you try to just use many channels, what is an issue? Flow distribution. How do you make sure that your flow, on paper, I can say every channel has the same flow rate, but in practice, how do you do that? The other that I will argue for as well is to actually increase the channel size. Okay, if you are looking for analytical applications, and then okay, you can go to sub-millimeter channels, even smaller, because actually this is good. You increase your sample volume. But if you want to think about production, there's no reason to go sub-millimeter. Actually, there are very good reasons to not go sub-millimeter because you might have some dirt, some impurities, and confuse the things. And I showed you this graph before where we had the mass transfer coefficients for 3 different channel sizes. We have actually done some work up to 4-millimeter channels. And in that case, okay, we lose a little bit of the mass transfer enhancement. But as we saw, it's not terrible. It's not that bad. But another consideration we should keep in mind is that we wanted to work in small channels for various reasons, because of the nice, defined flow patterns, lambda flows, perhaps. So there were various other reasons. So what we can say is that if we want to increase the channel size, we can increase up to a point that we do not lose the benefits of the microscale. Again, there is no magic number. It's not that 2 millimeters will do the job. If we have more viscous fluids, perhaps we can go bigger in channel size, or whatever. Some dimensionless numbers have to be considered here. So this is, I would argue, this is a good point to start. Let's scale up first, the traditional old-fashioned way we know, increase the size, before we go to scale out, to use more of those. Because, and this is again, I mean, we work in this area, but we have to be realistic as well. You can't scale out sub-millimeter channels. Flow distribution would be an issue, but also think of the actual device. It's a lot of material. There might be costs implicated on how to make it, what do you gain, and so we have to be practical from that point of view. The other thing we have started, I wanted to show it to you here because we actually started using it as a means of scaling up before scaling out, is to use these impinging jets. Yeah, so this graph here shows that, okay, if we increase the channel size, we lose some mass transfer enhancement, but we also, our area of plug flow changes. So again, we have to keep the benefits of the micro scale. And then we stop. Okay, let me see if that plays, because that's something Sweden found. I think, there was some, okay, there was a website here to attribute this. I should add it. So this is an impinging jet, and apparently, according to my student, it had been used for the COVID vaccine production. I can't believe him. It was on the there is somewhere the reference. So basically, impinging jets is something we have started working. Impinging jets have been there forever in fluid mechanics, usually in unconfined spaces to jets collide. And then as all these microscale things start coming up, people have started limiting the space where the jets collide. And this is how we work. We work with confined impinging jets. So what you get there is, as it shows here, there you have very fast mixing. And very quick, very fast mixing. And because of that, there have been applications on mixing, first of all, of fluids to fluids, crystallization, because you mix again, it's very good mixing. You have the nucleation happening, crystals forming, nanoparticle synthesis, which is related to crystallization, and so on. And we have used it for extractions. Okay. So if you want, this is a cool video. So yeah, I can give you the reference as well. So this is our impinging jets, and this is the first generation, let's say. And as you can see, it's a very simple setup what we did in the lab. And this was done by acrylic. That's our impinging jet here. And you can do, if you have some 3D printers, it's more common these days, you can also 3D print that. But in the end, we just connected those two channels. And our first generation is to have this type of configuration. So it's a T-junction where your side channels are very small, but the main channel is relatively bigger. So the fluids come in with quite a big velocity because they are in very, very small channels and they impinge. And because of that, that's the type of flow we form. So we form dispersions, coming back to your drops. But now we work more with these symmetric impinging jets. Because, with these ones, the mixing, there were some dead zones, and we thought we would try these ones. So I think I showed that to you before when we were discussing about the different measuring techniques. So this is the setup that we are using for the impinging jets, and this is the actual geometry of the symmetric impinging jets. So again, we have the two side channels here, they collide here, and then the mixture comes out both ways. And some properties. We have played a bit with this inlet diameter size. We've gone down to 0.25, and with this outer tubing size. So the inner ones are the two jets. The outer is where you, the jets are these two side channels. And the outlet is this main channels where we want our reaction to happen or separation. And this we use 2 millimeters because the other thing is I come from large scale flows. I have been working with the oil water flows, large pilot scales. One thing you have when you have two liquids is a lot of liquids. And if you start using solvents, it's a lot of solvents you have to do something about. And in fact, with these sort of systems, because the velocities are bigger, we start having a lot of fluids to deal with. So if it's not necessary, in this case here, we put the tubing small because it means we have to handle less volumes of fluids, which is important. Gas liquid flows are much easier. They only do this with air, at least at atmospheric conditions. Again, very briefly, I mean, these are things that you find in the literature. The thing is that we did a flow pattern map. In this case, I think we used some glycerol in our water. We had kerosene water with some glycerol. just to remove some of the reflections. So we were able to improve a little bit the images, and you get all these flow patterns again. The one we really want to work with is this droplet flow or some variations of that. And we are trying to do some studies of these flows. Yep, and that's what you actually get in the impingement zone. So what we have here, and the reason for that is to aid visualization, is that we have the aqueous solution comes from the jet underneath. The organic solution comes from the jet here. We have a lot less organic phase. And the only reason is that we are able to see, so we can take some images, some videos. Because if you increase the organic phase volume fraction, then it's very difficult to see. I mean, that goes back to what we discussed about imaging techniques. But imaging is marvelous, but once you start having interfaces, it's so very difficult to see what's going on. So there are various phenomena. So this is very interesting also just for studying how the mixing happens there before we move on to study the separation. And there is various phenomena, and it's very difficult to actually see what happens with imaging. So we had our hand at trying to do some modeling, and there are some modeling people at the back there, but maybe how to do it better. We did use tools available outside, and we actually used this CFD, which combines volume of fluid to discrete phase modeling. Because what we found here that was happening is that this phase comes in, because the other phase hits it, sort of spreads, creates a thin film, and then from the film, the drops escape, break. So basically, we have this sort of configuration. We have the aqueous phase coming here. It's colliding with the dispersed phase, the kerosene. It sort of spreads it out, creating all these thin ligaments from which the drops eventually break. So a lot of physics to study there, actually. And but to model it with CFD, it's kind of tricky because you model this part using volume of fluids. I think if you are not doing CFD, you're going to talk a bit about that today and tomorrow. But then what happens? How do you, if you have to create, you can stick with VOF, but then it gets a very demanding simulation. You get, you need to have very good resolution, very fine grids, etc., etc. And that's why it's good to bring in a different type of model, the discrete phase modeling that can handle better the dispersed phase. Of course, there are assumptions. You have to decide when you actually consider you allow when you move from the VOF to the discrete phase modeling, but it's doable, and we've got some results. They can be done better, but I think it's good enough to just show us some of the phenomena that are occurring. And it also shows that exactly this thing that I was describing to you before. You have the continuous phase coming in, colliding with the dispersed phase here. And here it is a velocity field, but that's what happens. So this is the movement of the flow that actually stretches the dispersed phase. And you can't do that. So yeah, I mean, with CFD, you can take images wherever you like. It's not like the camera that's fixed in one position. So this is what happens at the colliding zone, at the mixing plane, and how that changes if you move further away. It's nice images. So we got some results as well, and we were not terribly unhappy. I think I have some comparison. Maybe I should mention the comparison first and then go back to the results. So we did drop size distribution measurements with the CFD. So we measured the drop sizes that CFD gave us, and also with the experiments. And as I said, so the experiments are blue, the CFD is red. There are some variations. We were not very unhappy with the comparison. There are reasons why things could be improved in terms of CFD. In CFD, we didn't allow breakage after this impingement zone. After the first drops broke, we did not let any other breakage. We allowed only coalescence. there can always be a question of, even from the measurement on how small drops you can measure, you show the quality of the images, because we don't match a refractive index. So if people are interested into, let's say, the hydrodynamics, the fluid mechanics of this configuration, it's a nice problem. But again, I showed you this graph before, but it just shows how the jets work. So here we change the velocity, the total velocity, the two faces collide. That's how we define it. And what we get is, as you would expect, as your velocity increases, your drops get smaller, which is good, because it increases the interfacial area. And the other effect that we discussed a little bit is that when we use a very small and a very large fraction of the initial dispersed phase, then of course we are swapping which phase becomes the continuous, which again is expected. In all these cases, because we wanted to do that with imaging as well, we really needed to stay with low fractions of the dispersed phase. Otherwise, we wouldn't be able to see anything. But then again, in that system, we also use the ultrasound probes later on to get some information at higher volume fractions. Some more results on the average drop size. Are people familiar with this way of defining average drop sizes, outer mean diameter? Yeah. So this is one way to define drop sizes. So you use the cube over the square, the sum of the cube over the square diameters of all your drops. There is the arithmetic mean drop size as well. Various ways to compare drop sizes. And we have that again, the average drop size with the total velocity. And as you can see, we start D32, for example, from 200 microns. It can go down to, what is that, 50 microns. And also the interfacial area, because this is what we want to have as for mass transfer. I've shown you that. And again, you can, and this is available in the literature as well. People try to form some correlations on the drop size you get with the mixing intensity. And you can do it, it's a mechanistic model, it's a simplified model. It's like considering this is the mixing zone, the side jets, the main channels, and you can have some sort of energy balance here. It's mainly the kinetic energy that plays a role. And if we calculate this energy and we relate that and we plot it with the mean diameter, you get some sort of correlation like this. And what I'm comparing here is the two, let's say, results we got with this asymmetric and with which is the black point, and with the symmetric impinging jet. Okay, I miss here I should put that at the back. Yeah. Here.
Yeah, this one.
Uh-huh.
The area after fade, it's becoming constant despite the fact that the total velocity. So this is the limit to which.
It's basically what you get here as well, isn't it? That your outer mid diameter doesn't change after a certain energy input, which is related to velocity, doesn't change very much.
There's no point of operating after that. But
Yeah, I would say in this system. Yeah, I mean, at the moment in this system,
yeah,
because it's not that we have looked at different fluids, you know.
but once one of them will be a limitation which it can go to give it smaller.
It's not limitation. It's not. It's unless there is other benefits that are there is no point, because higher velocities means more power input pumping. Yeah. So if there is no reason to go faster, why go faster?
Will we gain out of
Um,
going faster?
I don't know. Yeah, probably nothing. So there is no point to go faster.
Pressure drop would be higher.
Yeah, exactly. The whole pumping, So yeah, exactly. So you can get information like that, really you are not gaining much if you push your system. Yeah. Okay, so this is the impinging jets. So we said that there are three ways to improve the throughput. One is to just the original channels, just make them bigger. The other is to use impinging jets. So in this case, we make our fluids flow faster when they join in the mixing zone. And the third is to actually do the scale out that we were mentioning. Just to say, there are some results that didn't include them. Maybe I should have done we have done a little bit of extractions with the impinging jets because we've been ourselves concentrating on the hydrodynamics more so far. But yeah, extractions are also quite good. And if you remember in the previous, just at the end of the previous presentation, we had some mass transfer coefficients for impinging jets. So they're actually doing quite well. You can even say that they're better. Again, you cannot generalize for the systems we've looked that have been looked, but they give you high mass transfer coefficients. One would expect that because it's a very, the interfaces are improved, in the specific interfacial areas are improved, the mixing is good, so you would expect to have better performance in that sense. Now, how much better to justify the fact that you lose some of the nice controlled flow patterns of plug flow? This is needs to be, yeah, it's a separate question.
Like I mentioned, won't be afterwards.
That can be an issue if you are worried about that, because the drops you form are really can't be very small unless the energy dissipation is different. I mean, these are not micro. This is 50 and this is average, which means you have some small, some larger. Yeah, but this one is now comparable. If you go to the 200, 150, 100 to 200 microns diameter is okay. Scale out. Have people looked at scale out at all? I mean, I saw some hands before. Have people come across this way of scaling up? Yeah. Okay, so who mentioned that before from that side? Have you worked with scale out? No. Yeah. Okay, so I'll mention a few things, and there is a lot of literature on scale out for single phase flows. So the idea there is what we were saying. Let's put a lot of channels together. Fine. But then the problem becomes, how do you make sure to make this thing work? You really have to make sure that all the channels operate at the same condition, which means for single phase flow that you have the same flow rate, the same residence time in all the channels. So how do you make sure that all channels have the same flow rate? Okay, one way is to use these sort of structures, the bifurcating structures. Yeah, because in this case, you put one fluid in, you split it into and then into and so on and so forth. And then you can also collect them if you want the same way, which has been suggested. It's perhaps used less, but I'm not entirely sure. But there are some issues here, which can be that if one channel blocks, for example, you lose the uniformity, you redistribute your flow. What we have seen as well is that if you're in very small scale, you cannot ignore manufacturing imperfections. So if your channels are not perfectly done, these non-uniformities can affect your distribution. Okay, so the other way is to use these sort of configurations, and then to ensure that the flow rate in this case distributes equally among the channels, people have gone back to use the resistance network modeling. Yeah, so basically this system here resembles electrical resistance circuits, where you're and basically they try to work with the equivalences between flow of fluids and flow of currents. Okay, so by having a system like that, you can go through the theory. The assumption is that if you have an electrical current, this is this configuration, and this is the equivalent electrical circuit, let's say. If you have a current of flow or of electricity, it should split in here. The sum of what you bring in should be equal to the sum of the flows on the other on these two sides. And also it's like using the Kirchhoff's law from electricity to balance the resistances inside the loop. So the two ideas are used the same way. And so there are equations. It takes a bit of time, but they can be done. They're not difficult in a way, just a lot of equations to solve. To actually decide using this approach, what should be the resistances in the main channels and in the side channels to ensure the distribution is equal, the flow distribution. So the whole aim here is to manipulate, to decide the resistances in these channels, in the main and the side one, and in the reaction ones and the side ones, to ensure that the flow distributes equally. Okay. And there are, if you go back to the literature, there are some ways. One is to have very big channels here. One is to use taper channels. There are various variations. You can do a lot using this approach. So this is for single channels. It kind of works. Now, I won't go too much on this, just to bring two concepts in. When we have single phase flow, we just have to worry about distributing the flow rate. When we have two-phase flow, we have to worry about distributing two flow rates, or the overall flow rate and the fraction of the two phases. Okay. And so we can't quite just follow the, let's say, the suggestions of the single phase flow. And what we try to do is to say that, okay, forget the very detailed math, just stay with the idea here, that if we have a 5-channel manifold, let's say, repeated, then let's say that to have this equal distribution, we would like in every channel to have flow rate of Q1 and of Q2 of the two phases. And be the total ones divided by 5. Okay. So we want in all channels to have these flow rates. Okay, this is our best, this is the perfect answer, the perfect solution. That's what we should have. However, if our distribution is not good, we could have these combinations of flow rates in the 5 channels, or how many it is here, 1, 2, 3, 4, 8, right? In the different channels. Ideally, all these should be here. In every channel, should we have just Q1 and Q2, no others. But we have variation because our manifold doesn't work well. So what we say is that there are, we have used this maldistribution metrics, one for the flow rate and one for the flow rate ratio or fraction. Ratio was easier to come out of the equations. And the smaller these are, the better the flow distribution. Okay, so the flow rate is basically how much this spread is. And the flow rate ratio is what is the angle, let's say, of or the slope of this line of the actual flow rates compared to the one we should have if all channels had this Q1 and Q2. Okay, use it as two metrics because in that case we do need to have to ensure two things are happening. Okay, so there is an extra complexity compared to the single phase flows. We decided to go with this approach. This is something we have developed in the lab. Kind of makes sense. So we have one channel, one inlet for one phase and one inlet for the other phase. We split them a lot of different, as many as we like. So each one has a manifold for the single phase, and then we join these single phases. Here is a picture that we did make it work, kind of works. I'll show you some results, and we've done that with dye. So you can see we managed to have plug flow in all the channels. And yeah, just for terminology, in all these cases, and I'll show you in a minute, we again applied this resistance network, but we had to worry about 3 resistances this time. Before we had the main channel and the reaction channels. Now we have what we call the main channels, one for each phase, a barrier, what we call the barrier channels or sections, where we have split the single phases, and the reaction channels, the red ones, where actually we bring together the two phases. Yeah. So we have to worry, that's all the resistances that go in. It's long, okay, there is a paper on that, you can have a look at it, but you can actually, by using these laws, which is that every, let's say, connection point, the flow rate should obey mass balance. So what comes in here as Q1 should be equal to this one and to this one flow rate. And also that in each loop, we should, the resistances, the pressure drop should balance. You can have a system of equations that can be solved. It's not as difficult. We just need to go through it systematically. And let me see. And we tried, yeah, what I wanted to say is that by using this, let's say, approach, we designed the manifolds that gave us the smallest metrics of flow rate distribution and of flow rate ratio distribution. And we now work, actually, we have been stuck with this manifold. We probably need to improve it. So based on these results, we designed this manifold with a certain, so what we had to worry about is how big is this channel? Because this is the frictional resistance you get here, the resistance. How big is this channel? Because this is the other frictional resistance. And if you want to think about scale up, and I'll mention that a little bit in the end, these channels here might be the ones you least want to play with, because what is a good size for these reaction channels is what your single phase work will have given you. You work on a single channel, you kind of optimize it, that's a good flow rates, that's the good channel size that I want, and I now want to replicate that. So basically, you don't want to touch that very much unless your whole system doesn't work, and then you go back. So basically, it's mainly these resistances to keep an eye on, because this is the manifold. This is your manifold, and this is the channel that you're actually wanting to do your operation. Yeah. Are you with me? Yep. Good. What about the others? Any questions? Why didn't you use that? What's that? Sorry, I'm not sure.
Similar to header, no?
Header, in header you will have varying pressure.
Mm-hmm.
Even first channel will have higher flow rate
Yeah.
as compared to the second.
Yeah.
Gradual pressure down.
Yeah. Yeah. Yeah.
How you regulate it? But in plenum box it's kind of you can say.
Oh, you mean designs?
Yeah, okay.
Let's not decide designs here, because you could. I don't disagree. You can include all that. So your model includes the equations of here. You don't have to have the same resistance here and here. If you change your channel size, your resistance here will be different to the resistance here. Okay, your system of equations will become more difficult. Yeah, so that's how they designed this one, actually. So here, basically, this resistance, to have this tapered, let's say, this resistance was not the same as this one. Yeah. So you can do all that. Yeah, it's fine. But you have to always think, if it is for application, you always have to think how easy doable something is. You can do that with tubes. If you want to have anything tapered, then of course your fabrication becomes more involved. It's not impossible. It actually might be, depending on the size, quite easy with printing today. Just bear that in mind as well. It's not good, it's not bad. It's just that one thing to consider. But yeah, you can do it because the model can accommodate these things. These resistance network models can accommodate these things. And yeah, the example is what I said here, that this means that the resistance in this part is not the same as the resistance in this part. Yeah. And actually finding resistances. So with these models, what you do is that you basically calculate resistances, which you then interpret as channel size, because you have a certain fluids. Yeah. So what the model finds for you is resistances, and then you say, okay, this the resistance. Should I put this equation? No, this here. The resistance is basically the frictional pressure drop. The pressure drop is the flow rates and some friction factor, effectively, which is the resistance, yeah, which includes the size channel, the flow velocity, yeah. Okay, so yeah, so you can have different geometries, and it's just that it's just that you work backwards in where you first calculate the resistances that will give you the distribution, and then you work out back to see what's the geometry there. Yeah, so yeah, you can. What I wanted to show you is very, very quickly that, and some considerations as well. Let me see, just to connect it nicely. Yeah, so okay, so then what happens is, and this is more like design considerations. We wanted to have a manifold for the lab that had 5 channels. We made one for 10 channels, but we're not using it so much because, as I said in the beginning, liquid means you have water, but you also have an organic. Organics you need to recycle because you cannot just put them down the drain, which means you have to start worrying about holding fluids, keeping them. So the higher the flow rates, the more fluids you are working with. So a manifold of 10 is a lot more volume than a manifold of 5. So we've done a lot of work with a manifold of 5, but it's nice to, of course, demonstrate it for bigger, especially for the industrial applications. So you make your design, and then practical considerations, if you go down that route, unless you make absolutely everything, then if you say that I need a channel that is 2.15 millimeters, and you go to catalogs, you will find out that there is a channel that is either 2 millimeters or 2.4 millimeters. Okay, so there is always a little bit of a back and forth. Yeah, this is not paper exercise now if you want to start making it. Anyway, so we made our manifold, and this is the best we came up, let's say, or a good design, because as you can see, we are very close to this optimum point. This is the flow rates we wanted to have in both channels. So this is kerosene water. So the question is now, okay, 5 channels, good. What happens if I go to 4 channels, 50 or 500? Okay, I can, again, the scale up issue. Would this manifold work? Yeah, I designed that for 5. We designed that for 5 channels. Can I just replicate these 5 channels and have something that works? Okay, so if I keep, that's what we found. If we keep the resistances constant, which means we keep the channels the same, yeah, that's the, we find out again in this map that, yeah, no, actually, with 50 channels, you get, this is the flow rates you get in your channels. That's your optimum, that's where you are. Go even more, you have, okay, so no is the answer. What we then decided, we went back, and you can get all these points. This is all paper exercise just by solving these equations again and again, the resistance equations, not experiments in the lab. If we keep the Mike distribution parameters constant, which means we can change the channel size, we actually get much better. Yeah. So basically, what it says is that if you kind of need to have from the beginning in mind how many channels you want to have in the end, to start designing your manifolds. And let me just introduce you this idea as well. And what we found is that if we, in the end, we want to have a system that has 50 channels, or not us, the industry, or 500 channels, it's better to design even the little one we do in the lab with these, let's say, requirements, with these channel sizes, and then check how bad is the distribution if we reduce that instead of 50 channels to 5 channels. Okay, so these are just some concepts that you can start playing with. So you don't design initially a manifold perfect for 5 channels, but you design it for 50, because this is the ultimate final requirement. But then you see, actually, does that 50, will that 50 give me good results with 5 as well? So I can keep working in the lab. So it's just some thoughts to have in mind when if you consider a scale up. And I think, no, yeah. So something else, bringing in pumping as well. The I'll explain you these two graphs. Again, it's a fancy drawings. Somebody's PhD was spent on those. It's not something you really do now in an hour, but it's just the concepts to bring in. What we did here is that we tried to do this parametric study, let's say. What if we change the channels? How much we affect this maldistribution? Basically, we did that first, and then we went to decide the one we made in the lab. So we played with the two resistances, the ratios. You remember we said we have the initial channels, the barrier channels, and the reaction channels. So we played with the ratios of the resistances because it was easier to get them from the model. And what you get here is a plot of this, the flow the flow rate ratio, the indicator. So what we got here that so this is the way the maldistribution increases. No, it's the other way around. It is the maldistribution decreases. Okay, that's what the arrows show. You go from increases. The smaller, the better. And then we did the same with and these lines here now show us the pressure required or the power required to run the system. Just want to show you these two graphs to see the effect as well. And it goes the other way. So basically, as we play with these resistances of the channels, we can read what's the power requirements. Power requirements come from, because we have flow rate, we have friction pressure drop, we can calculate the power requirements of a pump. I think we even added some efficiency here. It doesn't make a big difference. So basically, as you improve, let's say, the maldistribution, you pay on power requirements. Okay, that's the whole idea. So again, it depends on what you want. If you need to balance both these things, how much perfect my channels need to be, and I don't care how much power requirements are needed, or whether the power requirement is also a consideration, in which case maybe you can afford a little bit worse flow distribution, but at least you don't have to spend too much power. Yeah. Okay, so it's a complex graph, but I want you to see this difference in the arrows when we change the channel diameters, effectively, when we change the resistances. This is just channel diameters. Just to show you that we did actually do an extraction in a manifold, and this was with a company. I don't mention the metal here, but you can see the flow distribution we got. This is what we got in the 5 channels, the flow distribution for different flow rates, and then we did some extraction efficiency as well. And and that's the numbers we got. And then, again, we started thinking, because then it can be a little bit daunting if you go to industry, you say, I need, I can do you a very good extraction, but I need, I don't know, 200 channels. It's kind of not there yet. So what we found is that we played a bit with the metal concentration, because this in a requirement to get 6 kilograms per day of this metal separated. So we played a bit with the concentrations, extractant, because all these things can affect how much you extract in the end. The concentration, the initial metal concentration in the aqueous phase, the percentage extraction, how long your channel is, what volume fraction of the 2 phases you use. And we found that, well, we did all our work with 2 millimeters. We found out that we needed 92 channels. If we increase the channel size, we need 23 channels. And if we play with the concentrations more, then we can actually, with a 4 millimeter channel, we might only need 7. Okay. Yeah, and so this one is like 7 channels, which is more doable, something we plan to do in the lab now, because with 7 channels we can work, and I think even 28. And this is a pretty good diameter as well, because 4 millimeters, we just found out, we just saw, we have seen that we can still have plug flow even with not very viscous fluid, so it might be all right. Yeah, that's all I'm actually quite fast. I wanted to show on scale up. So I'm happy to take lots of questions if you have. Yeah, anything. We can go back as well. Might have gone a bit quick in the resistance network.
In maintenance point of view, you have to stand by at least 2 other units.
What do you mean for?
Because 2 pumps are running. They have one pump.
Pumps is a big issue. Yeah, no, you need to have pumps. Yeah.
All so one system.
So we managed to destroy one actually because we made our initial manifold out of acrylic. Would like acrylic is nice because you see, and you can also do. I don't know if people have access. We have a workshop. They have a CNC machine that could do acrylic. Now, how kind of, especially if precision is not required, there's some very good 3D printing going on. So you can actually do quite a few things with printing. You have to be careful with your materials because all these extractions, they have acids, they have oils. This is one thing to be careful of, but we are trying to see if we can do manifold printings rather than in acrylic. Acrylic is perfect, but can be quite sensitive. You know, to make a manifold like that.
Most of the manifolds are made of.
Yeah, I mean, metal is the other thing, but metal can be as tricky to make as acrylic because, metal is better in terms of preserving it. Metal, you have to be careful if you use acids. Okay, you have to be careful with metal. You can do a lot of things. Yeah, totally agree. I mean, you can have this thing that is metal and then your test sections to have transparent. With acrylic, one thing we found is that, of course, I mean, if people have done anything experimental like that, once you start, these are tubes that are not huge, might be, if I have the dimensions, a couple of 2, 3, 4 centimeters. If you start making holes on the acrylic, then you start weakening the material. It's more easy to break. Yeah, basically that. So, but once we go into this section here, then we use. So this is the one that we fabricate, and then we use a lot of tubing connections, which is very easy to change. So we don't do micro fabrication or fabricate, not micro, not even fabrication. So tubing connectors. So it's quite flexible in that sense. Yeah, you can change your tube size to 4 millimeters. You did it in the other day in your experiment. You change your tube size, so it's very yeah. And you have to start thinking about the pumps. That's the other thing because with there's always, it's like PAV. There is a fine line. You can't do standard PAV if you have a few millimeters or centimeters of your tube. If you are below millimeter, it's nice to do micro PAV, but there is the in between that sometimes is not very clear. Your channels are too big, too small to have a plain laser. So the same with the pumps here. It depends on the fluids as well. You can do, there are syringe pumps that are used extensively for microfluid, all this work, even if you go to 4 millimeter channels. And then you start talking about bigger pumps. And and there is a kind of, not a gap, it's an area where, yeah, you have to find the right equipment. It's neither small nor big, but it's somewhere in the middle. We've used, I mean, I'm happy to discuss pumps. So we've used Ecom pumps. We're using now is gear pumps might be good as well. So there are versions, just that at some point you cannot use syringe pumps anymore. Sometimes centrifugal pumps, they're good. They give the flow rates, might be, you have to check the pressure they can deliver. Yeah, so it's in between, I would say, scales that, yes, when you start doing the experiment, you have to think what's required. But fabrication can be done.
80% extraction, the recovery is 80%.
The recovery, yeah. This is not extraction efficiency, it's extraction. So 80% of the metal from the original phase went to, yeah.
But if you want to
You can go longer with the cube.
not tell the, because that will be limited by the equilibrium concentration, you cannot go beyond that. Have to take a question.
Say that, yeah. So yeah, exactly. Yeah. So that would be limited equilibrium.
So, I mean, in that case, how would you extend this flow extraction to multi-stage? Like with-
So then this is the other issue. I think I showed it a bit in the previous, a bit in the previous, no, here. There are various scenarios on how you can do this. You might need to go in the traditional mixer settlers. You have, you take the material out of one and you put it in the next stage. And you can then feed fresh solvent, or you can have some sort of counter current operation.
So you have to separate them. So
You might need if it's not enough, yeah. As you do in a mixer, in a mixer.
scaling out or.
Yeah.
Right?
So you have basically what I was showing you here. That is, let's make it bigger. So that's with this, it's all schematic because we have not done it in this scale. But basically, yeah, you have your batteries, let's say, of units of 5, 10 microchannels, yeah. And then you may need to do you remove, and then it's as I have it here, you remove. So, and you feed either the aqueous phase or the organic phase. So here the aqueous phase goes to the next, and then you feed fresh, organic phase. Or you can do it counter currently, which means this goes this way and the organic phase goes this way.
So the separation that we need for the two shapes.
In between, yeah.
In between.
Yeah.
So would you suggest a common separation or you suggest an independent separation? Maybe each channel have its own separation. And
That is something we have not kind of decided yet. So it depends. I think you can do both. I mean, at the moment, we just collect them all because we don't have many separators. You can think either way. I think a common is of batches of a few is more realistic. But of course, you have to account for this resistance into your resistance network.
Mhm.
Yeah, it's yeah, you can do. There are the separators I mentioned. They go. There are 3, I think, different sizes. The one we use is the smallest. We plan to go one size up to accommodate like 5 channels together, or the impinging jets actually as well, because that's higher flow rates.
So actually, because it's getting out, I was of thought because it might work outside.
Yeah.
The thing.
Mhm.
Can we use tensor and flow controller in individual channel?
What we have done, yeah, but you have to think a little bit of your. Yes, what we are doing now is that because with let's go back here then, since we're talking about yeah, gosh, no, I didn't mean that. I meant here. Yeah, because what we found out, and you see the result here. The camera can be quite difficult to use because I mean that's us trying to take photographs. You can't. So what we are doing now is for this system, okay, for plug flow in transparent channels. So we are developing light sensors, and we now have actually like a light with. So we have individual sensors in each one of them, but with the light, just absorption, like a simple LED. And we try to read the signal. So you get the signal from that, but from 5 channels at the same time.
Okay.
Yeah. Yeah, I mean, you can. The thing is to try to check, because with camera can be quite tricky. So to get these results, what we did is that we actually collect it at the end.
Right.
Yeah, per channel over time. Yeah, which is straightforward and
we
easy.
are not
But
really-
yeah.
Is there any issue in
Yeah, but you have 5 collecting tubes and you get at the same time. It's okay. I mean, it's a good reliable method. It's just that if you want to automate it a bit more and to get into more information, like plug size, frequency, etc., we are using these light sensors. But you can think of that with any other sensors. I mean, sound might be good as well. It depends. I mean, people are developing also conductivity sensors. There is work happening to actually investigate online. Conductivity can also give you perhaps the metals as well. But I know some work that some chemists are doing on that. So yeah, there are opportunities there, but yeah, the answer is yes. And because your channels are so well defined individual, you can actually pick up details of the flow with sensors. Imaging is the first thing, what's going on, right? Because that's what we wanted to see in the beginning. We could have all the red dye going here and none in the other channel. So it's a first, let's say, check is good. But it's very difficult with the camera to capture 5 channels, but also to have a good resolution because you need to zoom out to start getting information like plug size, in all of them.
IR sensor can be there
Sorry?
instead of camera. IR sensor can be.
Yeah. What we have is an LED, but you can have IR sensors, any light sensors. Yeah. So we done with the questions?